Thank you. And let me see if this works. Yes. Welcome to my PhD's defense, everyone. Irene already introduced the title, so I will not do that. However, I will start by explaining a bit about the project constellation. So this was an industrial PhD project, which meant that I was hired by SMP to do a research project here at the TU on these reinforcement products. What I have in my hand is an asphalt reinforcement grid that is designed to be installed inside a pavement system to delay the development of any damages. However, the issue and the reason why SMP wanted this project was that there's a missing a model that can actually calculate and quantify the effects of these grid inside pavement systems. So this is what we tried to do some research on. And when I say we, I was not alone in this project. I had the great honor of working with Klaus Olsen, Jan Levenberg, and Asper on this. And I want here to take the opportunity to say thank you for the good quality of supervision you gave me. Also, I want to acknowledge the Innovation Fund Denmark and SMP for funding this project. So, as I said, we work with these asphalt reinforcement grids, and I will try to start by explaining what is an asphalt pavement system. So, if we consider we have our local soil or rock, an asphalt pavement is built up by first placing some coarse granular materials, what we call a granular base or subbase. Then these layers are compacted and covered by some asphalt concrete. These added layers are all designed to carry our traffic loads. With time, these structures or roads, they deteriorate either due to external loading from our traffic or due to environmental conditions or a combination of both. I want to begin by looking into one of the critical responses that causes damage, one type of damage in our roads. So here I have indicated at the bottom of the asphalt a point. This point, or the critical response we look in here from a mechanistic point of view, is called a strain. And if I play an animation where load travels over, we will see that this point is feeling some strain history looking somewhat like this. So what this shows is that when the load is just in front of the point, we have some compression at the bottom of the asphalt. When the load is directly on top of the point, we transition into a tensile strain where it is extended and then goes back to compression again. Now, with time and many load cycles applied, some crack will eventually appear. And this creates a weakening point. These cracks develop and also other cracks develop around this critical area. And we see something we call fatigue cracking appearing somewhat like this on the surface. So this is bad for two reasons. One, when we have cracks in our pavement, it allows, or in our asphalt, it allows water to penetrate through and into deeper layers, which further accelerates development of damages. And also, as you can see, they generate some kind of potholes where asphalt actually flies out, and this is not super pleasant to drive on, and it's also can cause some be unsafe. Imagine this on the highway, for instance. Another type of damages are or critical responses that are linked to damage is the vertical strain on top of. In this case, I've indicated on top of the base, but in our substructure layers. And if I apply a load, we see some strain history looking like this, where we have our peak strain exactly when we are on top of this point. With time again, these strains develop some permanent deformation in our road structure, and we see something appearing like this, where we have these permanent deformations, and these appear on the surface as well. In reality, it looks somewhat like this. This is not good either because this traps water. It doesn't allow water to escape from whenever it's raining or whatever, and this reduces the friction between wheels and the road, and this is also super unsafe to drive on. So these are the type of damages, and one way to prevent or delay these damages types from developing is to use asphalt grid reinforcement products like this one. Also, I want to just note that I use further on this presentation the acronym AGR for asphalt grid reinforcement. So what are these grids? These are thin layers in some kind of mesh-shaped mesh-shaped arrangement. And they can be made of steel, polyester, glass fibers, or carbon fibers. These are designed to be installed near the asphalt layers, so either at the bottom of the base and covered by some asphalt. Can also be installed in between two asphalt layers. And finally, you can use these grids in existing pavement systems. Let's say in this case, we have a cracked old asphalt layer that we want to resurfacing, do some resurface maintenance on. So we remove a layer, you can place them grid and apply a new asphalt overlay. Now these grid solutions are of course not free, they cost some additional money. So a big question here in this project was, how do we do some kind of cost-benefit analysis? So how do we really quantify the benefits in terms of delaying these type of damages? In order to understand or to do this, we need to understand how do we actually determine the level of damage developed in regular roads. So here engineers, they follow some what we call a mechanistic empirical design procedure. Here an engineer would consider some inputs from the climate, what are the traffic we want to design a road for, and also which layers do we want in our roads and what type of materials. All this information goes into what we call a mechanistic engine or a computational model or tool, if you will, that calculates these critical responses I showed you before. And then we have some empirical formulas called transfer functions that translate responses into damage. And in the end, we can calculate how damage is developed, or how long can we expect the pavement to last until we see a level of damage. It's called mechanical empirical because we have two components, a mechanistic part and an empirical part. And what we want to develop here is a mechanistic part. So current mechanistic engines are based on layered elastic theory. This theory assumes a set of layers with a finite thickness placed on top of a semi-infinite medium. These layers are assigned some elastic properties denoted by E, Young's modulus, and a Poisson's ratio, V. Also, these layers are assumed to be homogeneous, infinite in all horizontal directions, and isotropic. Between two layers, we can define a bond ratio by inserting a spring that connects the two layers. This spring is characterized by a single spring constant, Kb. If Kb is a low value or approaching zero, it means that the two layers are free to slide on top of each other. And the other extreme case where Kb goes to high number approaching infinity, the two layers are locked and cannot slide on each other. Finally, the theory assumes a vertical load, circular load applied on the surface with a uniform stress distribution. The governing equations behind this theory allows one to calculate the stress, strains, or displacement response anywhere inside the system. Engineers use this framework to approximate a pavement system where they assume some loading corresponding to the standardized load, 10 tons, and they calculate the critical response inside at the bottom of the asphalt associated with fatigue cracking, or the vertical strain at the top of each sublayer associated with rotting. Now, this framework is quite a simplistic framework in the sense that we assume all layers to be elastic, but in reality, none of our layers we use in pavement systems are actually behaving linear elastically. Let's start with the granular materials. They have a non-linear behaving nature. What does that mean? It means that when we have a granular material and we compact it, we create some effective stress state. And for a given effective stress state, this material has a specific modulus assigned to it. But now if we apply a load, we increase locally under the load the stress state, and therefore it means that the modulus should increase. Now this effect happens, as I said, locally under the load, which means that under the load we have a higher modulus, but outside the loaded area we have a different modulus. And as I said with this theory, linear elastic theory, all layers have to be the same in all directions. So we cannot introduce a local increase in modulus. So this is super difficult to actually apply linear behavior in our layered elastic system. What we can do is to assume some average linear elastic modulus for these layers. Another feature that is not captured in our layered elastic theory is the linear viscoelastic behavior of asphalt concrete. What that means is that asphalt concrete has a modulus that is dependent on the time where a load is applied. So if we say that we apply a load and we assume it's linear elastic, it's basically saying that the modulus is the same at all times. But in reality, it's not. So this is how it's this is what we call a relaxation function or modulus, where suddenly when we apply a load, the concrete is behaving, or the asphalt concrete is behaving more like Portland cement concrete. And as we keep the load applied, the modulus will transition into a more granular-like behavior where it experiences a much less or lower value modulus value. Also in this case where there's granular behavior, it's also behaving nonlinear. To make it even more complex with asphalt, it's also dependent on the temperature conditions. The way to account or to visualize this is that when we increase the temperature, this time function shift to the right, and for a given amount of time when load is applied, we see that the modulus drops. Reversely, if we lower the temperature, we shift to the right here, and then the modulus increase. So these are some effects that need to be accounted for in this system. Also, because it's time and temperature dependent, we also need to simulate the loading conditions as a moving load and not as a static load applied to the system. So this is also a feature that one should include. And finally, how do we include asphalt grid reinforcement, which was the main scope of this project? So finally, we came to the objective of the study, which was to develop a mechanistic tool that can capture the reinforcement effect of these grids. It can capture other relevant features such as viscoelasticity and moving loads. And finally, most importantly, this tool we developed should be useful for engineers. So it means that when you use the tool, it should be quite fast in doing calculations. We cannot wait, I don't know, a day or a month for doing an advanced calculation. So this is what I mean by efficiency. And also, we should be sure that the model calculates correct. So that means validated compared to some experimental data. Another objective was stated to investigate some grid effects using the model. That means looking into how a grid can affect these critical responses and how temperature conditions and load travel speeds can have an influence on that effect. So the methodology was to come up with a formulation that includes the grid in based on our current mechanistic methods. Then everything was coded into a software. And this software will first check if it calculates correctly by comparing with other accepted pavement models, and also to check if it can reproduce measurements from reality. So let's start with the formulation. So the formulation we considered was based on layered elastic theory. We included the imperfect bonding between layers, moving and multiple loads were added to the framework, and viscoelastic layer properties is also included. So all these are something that people have been working on before. There's nothing new in how this is developed in theory. So we just took the theory and implemented it. Now the asphalt grid reinforcement is kind of the new thing in this PhD project. So which mechanisms do we want or do we have to consider in order to model the effect of a grid? First, we need to consider how do we introduce a product or a layer that is inhomogeneous, because the grid shape, it has some openings, makes it an inhomogeneous material. How do we include that in a framework that can only handle homogeneous layers? Secondly, how do we consider the bond when a grid is there? So you can imagine the bond between two normal asphalt layers where you have this interlocking between aggregates, which creates some kind of resistance, and so the layers cannot slide on top of each other. But if you introduce a grid, you can imagine that the grid will kind of break part of this interlocking and therefore reduce the bond. And this effect we need to be able to account for in the model. Finally, we have a nonlinear effect when we apply a grid, which we call the zone of influence effect. I will try to explain this mechanism by first considering the granular material and then say why it's important for asphalt also. So if you have a granular material and you try to apply an axial load and it wants to expand to the side, a normal granular material would allow to expand. But if you have a grid, you can see here that there will be some part around the grid where the aggregates interlock with the grid and are not allowed to expand outside. And this creates some kind of confinement zone within the zone. And that also means, if you remember back to the nonlinear behavior, that the modulus inside the zone should effectively increase. So how do we capture this effect? Yeah, and as I said, the reason why this is also relevant for asphalt is because we are, in some areas, we expect asphalt to behave more like a granular material, and therefore we should account for this nonlinear effect. So the way to do this was to first consider the homogeneity of the grid. We simply just smear out the grid into a homogeneous layer. So here we have two asphalt layers with a grid in between them. Each grid ribbon has a modulus and Poisson's ratio and some cross-sectional area. And we simply just take this cross-sectional area and reduce it into a homogeneous layer with an effective thickness. And to account for the bond, it's simply to introduce a spring stiffness above between the grid layer and the layer above, and another spring stiffness between the grid and the layer below. The way to emulate the zone of influence effect is to, if we consider two asphalt layers, they have the same, for simplicity, they have the same relaxation function and the same thickness. We account for this zone by subdividing the asphalt layers into some sublayers, and then the sublayers near the grid defined by some zone of influence thickness. We simply modify the relaxation modulus of this zone. And the way to do that is that in the area in the low end, for the low modulus, we say that this value, which is defined by E infinity, should increase with some constant multiplication factor we define as kappa. And this is, yeah, as I said, in the area where we expect granular-like behavior. So to conclude, we base our model on layered elasticity that can include elastic layer, viscoelastic layer, and moving loads, and of course the asphalt grid reinforcement that comes with 7 input parameters. All this was published in the International Journal of Pavement Engineering 1 year ago. Next step was to take this formulation and code it. I will just run over this quickly. This was coded in a MATLAB environment, and we created a code we called GridPave MM. So GridPave MM is based on another MATLAB code, open source code called ALVA, which solved the layered elastic equations, extended to moving loads and viscoelasticity, and of course include the formulation from an asphalt grid reinforcement. Also, the code can handle what we call fragmented layers that can be used to emulate the behavior of damaged layers. But I will not. I don't have time to cover the theory behind this. Just a side note. Then some numerical considerations were done in this part of the moving load and viscoelasticity to improve the computational efficiency of the code and make it calculate fast. There was actually a lot of effort put in here. Then the code was verified. That means first to check if it's numerically stable, all the things that I implemented. And secondly, to check if we can reproduce, which we could, measurements from other accepted design code, as well as some analytic benchmark solutions. I want to show you an example of how we can use the model. So let's say we want to design these two payment systems that are nominally identical, but one has a grid and the other one hasn't. So we simply give them some elastic parameters for the sublayers and a viscoelastic relaxation modulus for the top layer representing an asphalt. We apply a moving load on top of it, and we give some inputs for the grid. These are inputs taken from one of SAP's project. We assume perfect bond between the grid and the adjacent layers, and then we include this zone of influence effect above the grid, where we assume a thickness of 20 millimeters, more or less 2 or 3 times the aggregate size of asphalt concrete, and some kappa value 2, which means that we increase the lowest modulus from 100 to 200 in this case. The reason why we don't have the zone of influence below the grid is because usually in granular materials we have much larger aggregate, which can, in this case, we don't expect these big aggregates to be able to interlock with these small grid openings. So therefore it's neglected in this setup. So now I will show you how the horizontal strains appears for a situation where we assume a temperature in the asphalt of 30 degrees Celsius and a moving load speed of 5 kilometers per hour. So in the unreinforced case, we see a strain distribution somewhat like this, where on the horizontal actually we have the position of the load relative to the point of interest. And we can see as we go to 0 means that the load is on top of the point, and we have our maximum tensile strain. Now the same calculation is done, but with the grid inputs, and we can see a response where let's concentrate on the tensile peak strain. It's reduced, as you can see. If I calculate the relative percentage between these two peak strains, we see that the grid was able to reproduce this strain by 29%. I also here took a chance to model a case where we have a low temperature, so 5 degrees Celsius, and a fast-moving load speed of 80 kilometers per hour. So we move over in the other end of our relaxation modulus function. And you can clearly see that here I fixed the scale on the y-axis where we have the strain. And you can clearly see that for these temperature and load speed conditions, the strains are much less. This is automatically solved in the model because we have used the viscoelastic formulation. If I zoom in on the critical strains, you can see that the reduction of 8% is now the case for these conditions. So if I repeat this method and look into other critical responses, such as the vertical strain on top of the base, we can see that in the slow speed, hot temperature case, we have a reduction of 15% and only 6% in the fast and cold situation. And if I do the same on the vertical strain on the subgrade, we see a 0 effect or 3% effect. So there are some conclusions we can take from this synthetic study, I would call it, which is that we see that the grid has an effect on horizontal strains at the asphalt bottom, and also an effect on vertical strains on top of the base. Also, we see that, and these are of course somehow linked to fatigue cracking and rotting, and suggest that the grids have an effect on these. Also, it shows that the grid effects are higher in the case where we have slow moving loads, and also high temperature in our asphalt. Now, I want to talk a bit about how we then validated the model. Just a second. 20 minutes. Okay. Okay, good. Yeah, so about the model validation. Here we want basically to check if our model can reproduce some measurements from reality. In order to do so, as part of this project, we constructed a full-scale test setup. This full-scale test setup we call DTU Smart Road. It's placed here at DTU, not far away from where we are now. It's a 100-meter road stretch divided into 4 test sections. The old pavement, we milled off the asphalt in the old pavement. Then we installed some asphalt grid products in 3 of the sections at different heights within the asphalt structure. Here we used SMP carbon project some of you may have noticed that I put these products on the tables in this room. So if you are here, you can try to have a look at them. Also, we placed some strain gauges at the bottom of the asphalt and some temperature sensors between the asphalt layers to capture how the temperature conditions were within the asphalt during testing. So as I said, we use this SMP grid product, which is essentially made of some carbon fibers, which has a high modulus. These fibers are coated in some bitumen, and then some sand is kind of sprinkled on top of them, and the whole grid is placed on some thin plastic film. The reason why we have the sand and the film is because when these grids, they come in some rolls, they are a lot wider than this. This is just a sample. Then they can easily be rolled out. But if we don't have if you only have the bitumen, then kind of risk of sticking together, and that is not it's not possible to work with really. So these are only for installation purposes. The bitumen is also for installation purposes. Here I will show you a video of how we install a grid at our DTU Smart Road. As you can see, the grid comes in these rolls and it's dragged through some heating area where the grid is heated up. The bitumen changes its property and becomes more soft. And when it's pressed to the ground, it kind of sticks with the ground because it's been heated up. This is super important when for later installation purposes, that we have a good adhesion between the grid and the surface it's applied on, because when you come with the asphalt paver, you don't want the whole thing to be dragged up by the wheels. Here is a video of when we installed some of our sensors. So here you can see in each section, this is representing one section of 4, where we have 6 sensors in each section. 3 of them are oriented in the direction of travel, and other 3 are oriented transversely. And they also have different positions, as you can see. So these are, the cables are protected by some hand-laid asphalt. So when we run over with the paver wheels, we don't break them and then lose connection to our sensors. And yeah, you can see these are simply covered by some asphalt. Then we had a measuring campaign, where the measuring campaign was only carried out in 2 sections of the 4. One of the sections were the reference sections where no grid was installed, and the other section was the section where we have the grid at the bottom of the asphalt. So on a hot summer day where the asphalt temperature was high, we brought out a heavy forklift. This forklift is super big and has 2 axle loads that are more or less actually a bit higher than a normal truck axle load. So they are respectively about 11 tons and 12 tons. And you can see in this picture that shows a top view of the tire configuration, that on the front axle we have 4 loads or 4 wheels, and on the rear axle we have only 2 wheels. We asked the driver to drive a constant speed of 2 kilometers per hour, so it's super slow. And in order to model this afterwards, we needed to know how the vehicle was loaded relative to our sensor configuration. In order to do so, we placed a measuring tape on the surface of the pavement and some GoPro on the vehicle, and then we could kind of film whenever we cross this measuring tape, and then estimate this lateral position of the vehicle. All sensors were connected to a computer that was placed roadside, and here we have another video showing a clip from one of the passes from the POV of this computer screen. So I want you to focus on basically what happens on the computer screen as the load travels or passes by the sensor configuration. So as you can see, something clearly happens. There is a signal generated in the sensors. You can also see EL is kind of filming on some of these tapes to see the position of the vehicle. And yeah, if I stop here, you can see that clearly some peaks are deformed in the signal. If we consider the red curve, the yellow curve and the green curve, you can clearly see some peaks associated with these axle loads are generated. Then we wanted to check if we were able to reproduce these measurements with our model. First, we checked the unreinforced pavements. We consider which layers were used. We get some inputs from additional testing that we can use to predict the behavior pavement. We assume the loading configuration of this forklift, and we used information about the position of the forklift. Then we here I pointed out one of the strain responses corresponding to the rear axle load configuration in one of these longitudinal sensors, where I've plotted the strain on the vertical direction versus time. Then we tried to simulate this with our model, and we were able to get a match like this, where you can see that the first time it experienced some compression and transition into tension, the model was really good at generating the same response, but there is also something happening afterwards that the model could not reproduce. We expect some of the explanation for this to be due to some artificial drift in the sensors, which we see in many cases. So here is, I mean, we didn't only try to model one sensor, but we actually tried to have a model that could predict or reproduce the response of all 6 sensors embedded in the pavement simultaneously. So for the same model, we were able to get some matches looking like this, where, I mean, this was the best the model could do. I think it did a fairly good job, but in some cases, in many cases, we see the effect of some of this sensor drift, and also we see that there are some, if you concentrate on the peak strain, that there are sometimes where the model overestimate a bit what was measured, and sometimes it underestimate. But with this model, we were able to match these from the unreinforced case. We simply, in the reinforced case, we just wanted to add some grid inputs and then see if we could do a better fit than a model without a grid. So again, we considered the loading configuration and also the position. Now it's a new position from when the load passed by. This is the measured response to, again, corresponding to the rear axle load in one of the longitudinal sensors. And when we tried to, or when we calculated the responses with the grid, we get a match that looks somewhat like this. Now, if we compare it to a simulation where we remove the grid from the model, then we got this result. And I believe that this, and also we had what do you call it, an error calculating how well these curves are matched. And this numerical error was also saying that the model with the grid performed much better in matching reality than without the grid. Again, we did this on all sensors simultaneously, so the same model will predict the responses of all these sensors at different locations with different orientation. And these are the matches we got with the model. I can say that sensor 2 didn't work or survive the construction phase, so that there was nothing measured there. And if we again remove the grid, we can see in all cases the match between measurements and model becomes worse. So it's a clear indication of that the fact that we included the grid from the modeling formulation meant that we were able to obtain a better match. So to summarize the validation effort, we were, first of all, we constructed a full-scale test section, or actually 4 test sections here at this U, which we call VTU Smart Road. We were able to simultaneously reproduce responses from the model and compare, we were able to reproduce them with embedded sensor readings. And finally, we got an improved fit when including the grid formulation. All this effort was also sent or published in, actually 1 week ago, it was published in the International Journal of Pavement Engineering. Yeah, so I don't know, 5 minutes? Okay. Yeah, so to conclude this PhD project, I want to go back to the objectives that were stated. So in terms of the first objective, we were able to develop a mechanistic tool, which we called the grid pave. Grid pave can include elastic layers, fragmented layers, viscoelastic layers, moving loads, and of course, asphalt grid reinforcement. The code was turned out to be computationally efficient and also stable. And finally, we have shown that the model could both reproduce measurements from other accepted mechanistic tools, and also we were able to reproduce a measurement from or do a fairly good we were able to reproduce fairly good some measurements from reality. In terms of investigating the grid effects, which was the second objective, we could see that the grid, or we could model that the grid could reduce some critical responses, such as horizontal strains in the asphalt and vertical strains in the base, which are linked to fatigue cracking and rotting. And these results are consistent with other experimental studies. And finally, we also saw that this grid effect is dependent on the temperature conditions and also the load speed conditions. In terms of future work, what we could improve on with this project could do some more modeling, add some features from, let's say, horizontal loading, so we can also model how the grid effects are, how the grid can improve types of damages that are associated with braking. There's also, I don't know if there is an option, but one important thing to look into is how to include non-linear behavior. I put some question marks because I don't think people know how to do this in flared elastic theory. We can also do more validation. So we can use data from the two other test sections at DTU. We could also check for a situation where we have low temperature in our asphalt and we move with faster speeds to check if we actually see a lower effect of the grid as the model predicts. And finally, we can use we could also use data from other full-scale test sections. As part of this project, I've also been to the US and in Switzerland, where we did full-scale testing similar to what we had in the tube. Finally, future work includes also that we look into some of the grid model inputs. So how do we actually estimate this kappa value or the zone of influence thickness? Here we could imagine that this could maybe be checked in some kind of lab test. And also this interface bond, now I put it here in future works. Actually, we did work on estimating this bond level between two asphalt layers with and without a grid. And that was prepared for and submitted to a journal in a manuscript that is currently under review. So finally, what have this study contributed with? A new model for engineers that is both versatile, useful in the sense that it's quite fast, and also we have been able to validate the model, so it can calculate. It's a correct or can make a good estimate. And this can be used for cost-benefit analysis when people in the future want to have a grid solution or to consider a grid solution in their payment design. This model could be used to quantify these effects. And finally, manufacturers may be able to use the model in order to improve or develop new products, maybe look into how big the grid opening should be in order to make the best interlocking with different types of asphalt concrete, with different aggregate sizes, and also prevent too much deep bonding. And with that, I want to conclude or finalize this presentation by thanking all the people who were somehow involved in this project. The list is, I believe, quite long, which just proves how many people who actually needed to be included in order to do such a research. So yeah, thank you anyway, and good to see you all coming here to my PhD.